Hi guys, it's good to be back with you. Today we're going to dive into the amazing and freakishly weird world of clays, clay minerals, clay soils, and we're going to try to understand a little bit why clays are different than other soils. Engineers have understood for a long time that clays are different, but it really wasn't until the last maybe 50 or even 100 years max that we've understood why clay soils are different. So we're going to get really small today as we look at the molecular structure and what goes on inside of a clay molecule. But let's do a little bit of review first. Last week we talked about some of the basics of elementary soil mechanics and geotechnical engineering. We reviewed the concept of phase diagrams, and we also reviewed the concept of weight-volume relationships that we derive from those phase diagrams. We also talked about how we describe coarse-grained soils using a term called relative density, which is a term to describe the relative compactness of the soil particles. And if we can get soil particles as close together as possible, that would be a relative density of 100%. If we can pull them apart as far as possible but still have them touching so that the pore space in between the particles was as large as we could make it, then that would be a relative density of 0%. All coarse-grained soils fall between 0 and 100%. And then we talked about ways that we can describe fine-grained soils using consistency, and then characterize them using in terms of plasticity from what we reviewed as the Atterberg limit. So this would be the shrinkage limit, the plastic limit, the liquid limit, and understanding how terms that we can derive from these Atterberg limits, like the liquidity index, the activity, these types of parameters, they can be very, very useful for us in estimating or guesstimating what the engineering properties of a fine-grained soil might be. Now today, what we're going to do is we're going to learn about why fine-grained soils behave the way that they do, and why water in particular can make fine-grained soils and clay soils act a little wacky. So when we talk about clays and when we talk about fine-grained soils, we have to understand that mineralogy is really at the center of it all. Mineralogy is the primary factor, in fact, that controls the size and the shape and the physical and chemical properties of most soil particles, and including coarse-grained particles, that is. In cohesionless soils, so these would be non-clay soils, so these would be like sands and gravels. These types of soils, these particles are what we call inert, meaning they don't really chemically react with one another, though if there are certain mineralogies that if your sand particles or gravel particles were comprised of, might react to certain chemicals. But for the most part, you know, if we're talking silica-based or quartz-based minerals, which is the most common in these types of soils, they're very inactive, they're very inert. And so what that means then that all of the interactions that we see are predominantly physical in nature. They're governed by Newtonian forces. So this is stuff like mass equals force, or force equals mass times acceleration, those kinds of forces. Now, cohesive soils, these would be clays and plastic silts. These are a different animal. These types of soils are very, very small in particle size. How small? Usually less than 2 micrometers. A micrometer is 1/1000th of a millimeter. So that gives you an idea of how small these particles are. Now, when you're dealing with particles this small, Newtonian forces, while they're still in play, don't really matter very much because the mass is so small. So now we start dealing with different types of forces, electromagnetic forces, surface forces. All these kinds of things really start governing the behavior of these individual particles. And when you start governing the behavior of individual particles in mass or in large groups, then those electrical forces start governing the overall behavior of the entire material. A lot of chemical reactions are common in clays, and they can also react with other types of molecules, so things like water and things like electrolytes. So the thing that's unique about clay, and in my own practice I've seen it, is that you can have a relatively small amount of clay, like maybe 10%, 12%, and that little small amount can in many ways govern a lot of the engineering properties of that soil. For instance, if I have 12% of clay in a sand, a soil that's predominantly sand, that clay is going to govern, say, the permeability or the ability of water to permeate through the pore space of my soil. The permeability will be closer to the permeability of the clay than it will be the sand. And so that's just an example of how having even just a little bit of clay can completely change the engineering behavior of the soil mass as a whole. So to understand clays, let's go ahead and just dive right into the structure. And this is something we talked a little bit about in 341. Let's go a little deeper. So we're going to start with two basic molecules, or I guess this is a molecule and this is an ion. Okay, so the molecule, we call it hydroxyl. It's a combination of just one hydrogen and one oxygen. If it had one more hydrogen, it would be water. But it's lacking that hydrogen. So a hydroxyl ion has a net -1 charge. And then we have cations. Now, cations are positively charged ions, meaning they have an excess of electrons. They want to shed those electrons to reach a balanced valence, and so, or I should say, a complete valence. And so these types of materials, they're usually metals. They want to lose those electrons, and so they're looking for molecules that have net negative charges so they can give them some of their electrons. So these are the two basic types of particles we're dealing with. Now, you introduce those particles like a giant party and they start to mingle and stuff starts to happen. They start to arrange themselves. And the way that they arrange themselves, and you know, we don't do this, they do this naturally themselves. They arrange themselves into two fundamental shapes. The first shape is a tetrahedral shape, meaning it has 4 sides. 1, 2, 3, and then on the back side here, 4 sides, kind of like a pyramid, right? Now, this particular molecule, we call it a silica tetrahedron because quite often that metallic ion in the middle there is a silica ion, which has a +4 charge, meaning that each one of these negative charges that's on here satisfies it, and it becomes a happy and a satisfied molecule. But it can also have other cations. It could have aluminum in there, or it could have magnesium in there. And depending on which cation is holding this bad boy together, it will affect how different tetrahedra are going to join and link together, which we'll talk about in a minute. Now, the other fundamental molecule that gets formed is an octahedron, meaning that it has 8 faces. I'm not going to color those in because that would be too confusing on just this flat screen of mine. But you get the idea. This shape is going to have 8 faces on it, and again we have our metallic ion, our cation in there, and then it's surrounded by the appropriate number of hydroxyl ions. Okay, so depending on the net charge that results from these molecules that form and the cations that are basically holding all these things together, they start to arrange themselves into sheets like this, which means that these different tetrahedra may start to share hydroxyls. And these shared hydroxyls begin to link them together. And it's the same with these guys too. They start to share hydroxyl ions, and in sharing, they begin to develop these big flat sheets. So they begin to arrange themselves in these different sheets. So they can form what we call a silica sheet, or they can form what we call an octahedral sheet. Okay, so we have silica sheets and octahedral sheets that are forming all on their own. So a way that we like to represent these sheets is with shapes, and often with a symbol in the middle of it. That symbol represents the maybe the ion or the metallic ion that's in there. So an S, we might say, is silica. And so this shape here, this polygon shape of a trapezoid here, represents a silica sheet. And then the octahedral sheets are represented with a rectangle. Now, often we'll see in the rectangle a G for gibbsite or a B for brucite. G for gibbsite or B for brucite. Again, they represent octahedral sheets, but the difference is what type of minerals in the middle of them. So either we have aluminum or we have magnesium inside those octahedra, okay? So if we have aluminum, it's gibbsite. If we have magnesium, it's brucite. So we have these sheets. These sheets then begin to stack and begin to also share these hydroxyls on the top of the sheets. And they start to share and get together and form bond. They bond and they begin to stack. Now the two types of bonding they can use what's called either ionic bonding. Ionic bonding is the same as hydrogen bonding. It's where hydroxyls get together and they share a hydrogen atom. And they're very strong bonds. It takes a lot of energy to break an ionic bond. But the other is called covalent bonding. And covalent bonding occurs when we have cations that are like the glue between two silica sheets. And the silica sheets are just sharing some electrons from that cation, but it doesn't take near as much energy to break apart a covalent bond. So with these types of bondings that can occur, and just depending on what's available in nature at that spot, they start to form themselves in the manner that requires the least amount of energy. And they can form or bond themselves very, very tightly. Like, so let's say there's not a lot of free cations that are floating around. So they might form themselves in this manner. And if that's the case, you get very, very tight stacking and a lot of hydrogen bonds. So you get a relatively inert clay material in this instance. This would be a clay. This stacking here represents a common mineral we've mentioned in the past of kaolinite. And you'll remember that kaolinite is something that's used, for instance, as an additive into food. If you ever have heartburn problems and you take Rolaids or Tums, that one of the main ingredients in there is kaolin. And that's because kaolin is very inert, very inactive. It can just absorb all the nasty acids that are in your stomach, and then you just eject them with the rest of your food through a bowel movement, and you're good to go. Now, if we had, let's say in this particular environment, we had a lot of potassium ions available as well. So those potassium ions may situate themselves in this manner and form a link between these different silica sheets. And then you kind of get this sandwich effect. So if this is what you're dealing with, then this might form a mineral that we call illite. Illite is a little more reactive than kaolinite, And depending on the cations that are available, it can actually become quite reactive and active in the presence of water and other cations. But for this example, if we have potassium in there, it's really not too bad. If, let's say, we don't have a lot of cations or a specific set of cations to link these together, but we do have a lot of water, then we can get an arrangement that looks like this. And so the interesting thing here is this silica sheet here and this silica sheet here, they don't like each other and they don't want to bond. So they need something in between in this space in order to bond them. So they allow whatever they want or whatever they can get their hands on into that space so that they can form a covalent bond with it. So it could be water, it could be different cations if suddenly those cations get introduced. The point is it's very, very reactive. And anything you introduce is going to get pulled in to that space between these molecules here. So what type of mineral is this? It's very, very reactive. This would be an example of montmorillonite. Montmorillonite also is known as bentonite, sometimes known as smectite. The idea is, though, that this clay mineral is very reactive and it absorbs a lot of water. It's one of the reasons why if you go to the spa and you go get a facial done and they put a clay mask on your face, guess what? That clay mask is comprised of montmorillonite. It sucks all the oil and the impurities out of your skin. So we can use electron microscope images here, and we can look at different clay mineralogies, different clay types. We can make a game out of this. If play it if you want, but the idea is you can see different clay minerals look differently on the molecular level. For instance, this first one here on the top left, it looks very jagged. You can definitely see platey structures, things together, but you can also see a lot of void space and flakes in there. This is an example of illite. The second image on the top, this image here shows very uniform flakes, very uniform sheets that are tightly stacked together. They almost look like a stack of like Post-it notes or something. This type of clay is kaolinite. Very tightly stacked minerals that are linked together with hydrogen bonds. Then we have this this freaky looking image here where you can see almost like a honeycomb shape. Lots of space. It looks like a very spacious network kind of structure. This is montmorillonite. So you can see montmorillonite, there's lots of room for stuff to get sucked in and brought into the mass there. Now, what about these other three? Well, the reality, folks, is there are dozens and dozens and dozens of different clay minerals. Every imagined combination of a silica sheet, an octahedral sheet, and different cations can form a different clay mineral. And just depending on what nature provided in a particular area, it can form different clay mineralogies. So, for instance, this one on the bottom left is a unique and an interesting clay mineral. It's called halloysite. It's not necessarily rare, but it's just different because its molecular structure causes that these sheets roll themselves up into tubes. But if you dry the clay out, or if you heat it up, in essence, if you dry it out, it will cause those tubes to unravel. So the water is what's really holding those sheets together in their tube form. So if you dry it out and then try to remoisten it again, it will completely change what type of clay it is. It'll go from halloysite to a kaolinite just by drying it out. This clay mineral here in the bottom middle, vermiculite, it's a particularly nasty clay, has a lot of problems associated with it. We don't need to get into those now, but it's just another clay mineral. And then this one on the bottom right. This is a really interesting picture, and I wanted to show it to show that rarely do we have just a pure clay mineral. Oftentimes it's a mixture. So in this one we have a mixture of kaolinite and the clay mineral chlorite. Look, here on the top we have kaolinite. It's the same appearance as this stuff here. See how it looks the same? But down here on the bottom we have much smaller sheets. They're more tightly compacted, but you can see that they also look like Post-it notes, but just in a smaller version. So it's like big Post-it notes and small Post-it notes. This mineral on the bottom is chlorite. So it has a lot of properties similar to kaolinite, but it's just a different mineral, a different clay mineral ultimately. So this gives you an idea of just the vastness of what's out there. And geotechnical engineers become familiar with these different clay mineralogies. If you practice or work in a particular area in your profession or a particular geographic area, you will most likely become very familiar with the clay minerals that are predominant in that area. Now, if we were to just try to diagram what might be in one of these electronic microscope photographs, we could try to sketch it out and diagram it, and we can classify some of these different particles and their conglomerations with different terms. So this is a figure that I pulled from Holtz and Kovacs, a very, very wonderful geotechnical reference, and I highly recommend that you get it. It's called Introduction to Geotechnical Engineering. So this is just a schematic diagram of clay particles, okay? Now we have, in this, we have space and voids, like right here, but then we have a whole conglomeration of particles, and that's what each of these three represents, okay? If we zoom in a little bit, it might look like this. So it might look like a scaly appearance. And if we were to zoom in on those scales and we were to zoom out, this is what it would look like. So on the smallest scale, we have individual sheets that are stacked together, like what we saw in the kaolinite. Those little individual sheets stacked together are what we call a domain. It's a domain of clay molecules, okay? If we then take a couple domains and we conglomerate them together, it might form a little pile of domains that we refer to as a cluster. So a series of domains connected together or bonded together creates clusters. Now clusters bonded together form what we call PEDs. Okay, so PEDs are just a whole bunch of clusters bonded together, and that's what we get. But it's not just clay molecules that are in there, because in addition, we could see probably some larger particles that were floating around among the clay particles. And these larger particles, they would look like, I mean, giants compared to the clay particles. Those folks are what we call silt. So those are silt particles. And silt has properties that are more similar to very, very fine sand. And that's essentially what silt is. It's just sand that has been eroded or ground so finely that it's beginning to approach the scale of clusters, basically. Okay. And then within this matrix of clusters and domains and silt grains, we can have what we call micropores. So micropores are like the empty spaces in between the PEDs. So they're very, very small, but they represent empty space. And then, like I mentioned before, you can still have these macropores. So that's like this number 6. And so you can have a pretty big void space. So if we were to combine it all together, this is what these pictures right here. This is what it would look like if you were to zoom in and see a clay molecule up close. That's at least a schematic of it. This guy here on the left represents a flocculated sediment interspersed with silt grains. So flocculated means that the particles are bonded together, they're touching, you got a lot of stuff, but you have a lot of pore space in between, okay? This figure on the right down here, this guy represents the sediment after it's been subjected to overburden or other stresses that have resulted in the reorientation of the domains, clusters, and PEDs into a more parallel or a dispersed state. So do you see how this is basically just a squished version of our original flocculated microstructure? So here's a table pulled out from another wonderful geotechnical reference called Lamb and Whitman, Soil Mechanics, originally published in 1969. I heard this book went out of print, and I was really sad to hear that because this is a geotechnical classic, and anybody who's a geotechnical purist should have this book sitting on their shelves. So anyway, this table comes out of their book, and I've circled a few things that I want to point out and we'll talk about. This table and the table on the next page goes through a whole variety of clay minerals, and it shows the structure of those clay minerals in terms of the symbology or the symbolism that we already talked about. So you can see the octahedral sheet, that's with a B, so that's brucite. This one has a G, so that's gibbsite. If you see an open circle, like right there, okay, that's going to represent magnesium. If you see a closed circle, let's see, those maybe on the next page, closed circles like that, that's going to represent potassium as the cation that's doing the covalent bonding. So you can see all of these are just a different combination, a different way to shuffle the cards, so to speak. Okay. What else do we have in here? Something we'll talk about in just a few slides. This is the rules, or we'll say the most common means of what we call isomorphous substitution. Again, we'll talk about this in a few slides, but in a nutshell, isomorphous substitution is swapping out one metallic cation for another metallic cation. And it's the basis for a lot of chemical soil improvement to troublesome clays. Here's a description of the linkage between the different sheets, whether you have H bonding, so H bonding is, again, ionic bonding, or you have valence bonding, which is the same as covalent bonding, okay? Now this is really interesting, and I hope that you guys spend some time and look at these numbers here. Specific surface. The way I like to think of specific surface, if you were to take 1 gram, 1 pure gram of that material without any other materials in there or any impurities in there, just 1 gram of pure, let's use a halloysite as an example, halloysite, and you were to pound it with a hammer flat, completely flat, this number right here tells you the surface area in square meters that you would have from that 1 gram of material. And this will blow your mind for a lot of these, because you're going, wait, 1 gram? It's like a cube of sugar. That's not a ton of material at all. And this is what I'm talking about. Clay is freaky stuff. There is so much surface in a clay molecule, and that's why these electromagnetic forces govern its behavior. So we're going to come back to that and look at some of these, but I still want to introduce what these different values in the table are. This right here, potential exchange capacity in units of milli equivalents per 100 grams of material. This is essentially an indicator of how reactive that material is, or I should say how responsive that material is to swapping cations if you were to introduce new cations to it. The higher the number, the higher the desire or potential for that material to swap its cations, okay? Now, you'll notice this also says exchange capacity, but we have two differences. We have potential and we have actual, okay? The difference here is the potential means essentially worst case scenario, this is the highest exchange capacity we could get. If we were to take just the most reactive cation and throw it in there, this is what we could theoretically get with this type of mineral. This value on the right represents the more, what we tend to see with actual minerals that are available in the real world. Okay? So you can see with a lot of these, at least on this table, those values are the same. The worst case scenario is what we tend to see with the minerals that are available in nature. Because we tend to focus a lot on the three main minerals of clay, kaolinite, aeolite, and montmorillonite, I've taken the liberty of just circling these values in the table and bring your attention to them. So don't pay too much attention why kaolinite is circled. Going to the next page of the table, you can see I've highlighted aeolite and I've highlighted montmorillonite. Now I put a little star by montmorillonite because I want to go and I want to point out one thing. Check that bad boy out. Check that bad boy out. 800 square meters. 800 square meters. That's almost a football field in 1 gram of montmorillonite. If you were to pound that montmorillonite completely flat, that's how much surface area is in 1 gram of montmorillonite. And that's why, folks, montmorillonite is so stinking reactive with various cations and with various water and anything. There's so much surface area that it can react with, okay? Also, this is interesting. Look at aeolite. Worst case scenario, aeolite is an exchange capacity nightmare. It could exchange with anything. It's crazy. But most aeolite isn't that bad. Aeolite in the real world, it's usually around an exchange capacity of 25. This is why, if you look at these numbers right here for vermiculite, this is why I was kind of queasy when I mentioned it. Yeah, vermiculite has a very, very high exchange capacity. It's trying its best to get rid of that cation it has and swap it with something else. And another one that has a high exchange capacity, of course, is montmorillonite, which is actually good news for us because a clay mineral that has a high exchange capacity means that it's just begging for us to fix it, to swap out that cation and to give it something that makes that clay mineral less reactive. Anyway, have fun with this table, kind of go through it, look at it. It's pretty interesting. Okay, as promised, I wanted to dive into this topic of isomorphous substitution. Isomorphous substitution, in essence, is just the exchange of cations, but without changing the structure of the clay molecule. In other words, we're not going to blow up the tetrahedra or the octahedra. We're not. That cation is simply going to slip out, and the new cation is going to slip in, and everything's going to be fine. So it's like doing a trade on a professional sports team, right? You're just swapping players. That's it. So what this will do, however, is because different cations can have different charges. For instance, if I swap from magnesium that has a positive 2 charge to, say, sodium, which has a positive 1 charge, it's going to change the overall charge of the entire molecule. And that's what's going to cause a change in the fundamental behavior of that clay material, which will, in essence, change its engineering properties. You following me? Okay, so here's how this works. Isomorphous substitution is going to occur when we replace cations with cations of a lower electrovalence. So like a lower charge. That's how it's always going to work. Magnesium is going to be replaced by sodium. Aluminum is going to be replaced by magnesium, and so on and so forth, okay? So some examples. Say I start with silica, and there I go. You can see I have net zero charge, but we start introducing a whole lot. Whoops, sorry. We start introducing aluminum to the mix. Start introducing aluminum. Guess what? We have isomorphous substitution. The aluminum swaps out the silicon, and now we have a net -1 charge on our entire molecule, which will cause a change in its behavior. Say we had aluminum and we introduced a whole bunch of magnesium into the mix. Well, that's going to cause isomorphous substitution, and now we have again a net negative charge, okay? Now you may be wondering, hold on, aluminum is a +3, how come I have a 0 charge right here? It doesn't make sense. Well, that's because maybe this is an octahedra, not a tetrahedra, okay? So from that table that we talked about, the Lamb and Whitman table, the exchange capacity in terms of milliequivalents per 100 grams. This cation exchange capacity quantifies it's a measure of the net negative charge on the soil particles resulting from the isomorphous substitution and the resulting broken bonds that occur at the boundaries because we broke up the marriage of the previous cations with the hydroxyls. So it's in terms of, again, these units of milliequivalents per 100 grams of soil. And it's intended then to just provide a measure of the potential for us to perform an isomorphous substitution. Here are some general rules that govern cation exchange capacity. Okay, so first of all, smaller cations are going to replace larger ones. Sodium is going to replace magnesium. Magnesium is going to replace aluminum, so on and so forth. Now, higher valence cations replace lower valence cations. If you have cations that have they're clunky because they have tons of shells of electrons, those are always going to get replaced by more I would say efficient ions, okay? They're higher valence. And you'll have to go back into, if you're confused by what valence is, look it up on the internet or go back to your chemistry textbooks and you can get a refresher on that. Now, what's interesting is even if we are trying to replace, let's say, a higher valence ion with a lower valence ion, we can do it if we just saturate the dickens with that lower valence ions. If we just saturate it with those cations, even though there may be higher valence cations already in there, the lower valence cations will force the higher valence cations out. Think of this as like, say you have a really strong army that's holed up inside of a castle and they're defending it, and a weak army shows up to try to displace the strong army. There's no way it's going to happen. Strong armies displace weak armies. But if you bring enough weak armies to the war, or to the battle, then eventually they'll overpower the strong army and will be able to take over the castle. That's a way I like to think of it. So, right here, folks, is essentially the general replacement order, assuming we had equal concentrations of all these different cations. Sodium will always replace lithium, will always replace potassium, will always replace rubium, cesium, then magnesium, then calcium, barium, and so on and so forth, all the way up until we get to thorium, okay? And it could keep going, silica, and so on and so forth. Now, in terms of cations that are the most common for isomorphous substitution, these are the ones that we tend to see the most: calcium, magnesium, sodium, and potassium. Because they're the most commonly found cations in nature. So what kind of effect does isomorphous isomorphous substitution have on the engineering properties of clays? Well, let's look at it in terms of our Atterberg limits and the resulting plasticity index. So you can see for different clay minerals, montmorillonite, illite, kaolinite, and a different mineral we haven't mentioned yet, but it's a fun one to say 100 times, Atterbergite. I should get a cat someday and name it Atterbergite. That would be fun. Anyway, exchangeable ions represent the ion that is currently inside of the tetrahedra or the octahedra. So we have sodium, we have potassium, calcium, magnesium, iron, and then you'll see iron here with a star. And what this means is after 5 cycles of wetting and drying, meaning, what if we had like a halloysite type soil where we dried it? Will that change the properties of it? Okay. So here's what we see. Check this out. With sodium, in every single instance, look at the liquid limit, 710%. 710%. You guys know what that means? That basically means that the moisture content, the water content of the soil is 710%. That means the weight of the water is 710 times the weight of the solids in that clay mixture before the soil begins to act soupy like a mud. You think about that. That is incredible. And in every single instance, look, sodium is either tied for or has the highest liquid limit. Okay, and why is that? Because when you have the sodium cation in there, it makes the clay mineral the most reactive to the water, okay, and to the other cations that are there. A little bit less reactive is the cation of, I need to sneeze. Okay. Bless me. I'm sorry. I hope that you weren't wearing headphones when that happened. If you were, don't leave a nasty comment. Anyway, potassium. Here we go. Potassium. It is also very, very high. Look at the liquid limits. But they're not as high as sodium, except in that instance. Pretty close right there, but still, it's lower. Meaning it can't hang on to water as effectively as the sodium cation can. And so on. Look all the way. Look what happens if we get all the way to iron. Look at the difference. We have fundamentally changed that clay mineral's ability to retain water just by changing the cation. And we see the same thing happen with plastic limit and, of course, plasticity index. So, what does this mean? It means, my friends, that if we have a soil, a clay soil, that demonstrates engineering properties that aren't very desirable, say plasticity index. If we can perform isomorphous substitution and get a clay mineral in there that will give us an engineering property that's more desirable for what we want, we can in essence change the mineralogy of that clay and change its behavior just by introducing new cations. In terms of Atterberg limits and these different clay minerals, Holtz and Kovacs showed us, they plotted data from Casa Grande and also from Jim Mitchell from 1976 that showed where these different clay minerals tend to plot on Casa Grande's plasticity index chart, okay, or the plasticity chart. So halloysites kind of hang out in this region. Kaolinites kind of hang out in this region right here below the A line. Illites are right above the A line usually, okay? And montmorillonites, they're usually way up here, up by the U line. And then we have chlorites. Chlorites can kind of hang out right here. And so on and so forth. So you can kind of see how different minerals hang out in different areas on Casa Grande's plasticity chart. Well, what's the fundamental mechanism in all of this? What's going on? Okay. Well, the fundamental mechanism is the bonding that's happening. We have ionic bonding, covalent bonding, all sorts of those things going on. If we zoom out though and understand, okay, if I'm introducing water to the mix, how come montmorillonite goes absolutely berserk and crazy, but kaolinite doesn't? What's going on? Well, it all relates to something we talked about in 341 on the very first day. We call it the double layer. And the double layer is just a simple term that we use to describe this enormous cloud of ions that get attracted to and attach themselves to the exterior of the clay molecules, to the exterior of the PEDs in that micro matrix, okay? So here's what happens. Here's the surface of the clay particle. Now we've drawn it nice and neat like a little rectangle. The reality is it's going to be all sorts of jagged, okay? Just like you saw in those electron microscope figures. And each of these negative charges is essentially a hydroxyl ion that's hanging out there just begging for an ion to come and attach itself to it. So that's what happens. If you have any free floating or any free available cations, they're going to come to the party. Cations are net positive charged ions. They're going to come and get attracted to those negative charges. And then, because you have now all this positive charge, this cloud of positive charges, that's going to attract a cloud of negative charges that are going to come and attach themselves to the positive charges. And what you end up with is this giant, like a cloud or a shield or a buffer of garbage ions that are just attaching themselves to the clay molecule. And they go for a ride. The clay molecule just drags them around, okay? If we look in and understand what's going on molecularly, what's causing those attractions, okay? If we want to see, or if we want to look at the concentration of ions that are there versus the distance from the surface or the edge of that clay particle, look at this. Cations, we have the highest concentration right next to the surface of that clay particle. That's because we have covalent and ionic bonding happening between the cation and the exposed hydroxyl on the edge of the tetrahedra or octahedral sheets. And so we just get a ton of cations there. Now, we get the least or the fewest amount of anions or negative ions right next to or closest to the edge of that clay molecule. But you still can get a few. The further we go away from the edge of that molecule, our population of anions increases, but our population of cations decreases. And eventually we get to a point where they're the same. And at this point, this means no attraction, really. And whatever ions are there are just floating in space. They just happen to be there. So this distance right here, that represents our double layer, okay? What about water? Well, water is a unique molecule because it's what we call a dipole or dipolar molecule, meaning that it's not balanced. It's geometrically not balanced. You have one side of the molecule that has a net negative charge, and you have the other side of the molecule that has a net positive charge. Now, combined together, they have no charge, but it's not like the charges are equally balanced. So, what does that mean? If I have my clay particle surface there that has a net negative charge, the positive side of water, meaning the hydrogen side, is going to pull itself and attach itself to those hydroxyl ions on the sheets, okay? And it will have covalent bonding. Another option, though, is if, say, I have a cation, like aluminum or magnesium or calcium, and it decides to attach itself to those exposed hydroxyls. If that's the case, well, now the negative side of the water attaches itself to the cation. So that's going to be the oxygen side of the water, which will then leave the positive side exposed, which will attract additional anions. Now, a third possibility that happens is this clay molecule needs another hydrogen atom to complete a sheet, or to complete, in other words, it needs another hydrogen atom for a hydroxyl ion, okay? So what it can do is it just pulls in water and it fuses. It does a hydrogen bond. And if you get a hydrogen bond, then basically that water is not going anywhere. It's staying with that clay mineral forever. And so these are the three mechanisms that water can attach itself to clay through the double layer. You have, again, positive end of water attaching itself to the negative clay particles. Or you have the negative part of water attaching itself to an attached cation. Now, both of these right here, okay, both of those options, the water can be removed from the clay particle by drying out or heating it up, but you can get the water out of there. This third option, the hydrogen bond, you need a tremendous amount of heat and energy to bust that bond and to free that water molecule from the clay sheet, okay? So what kinds of things affect the thickness of a double layer? Well, the double layer is proportional to the following things. First of all, it's inversely proportional to the concentration of cations. So in other words, the more cations I have, the smaller the double layer. Interesting. It's also inversely proportional to the valence of the cations. The higher the valence, the smaller the double layer, the thinner the double layer. Okay. The size of the ion of the clay molecule affects the size of the double layer. So, for instance, here's kaolinite, and check that out. We have 400 as our units right there. And here's montmorillonite, a much smaller ion. Its double layer is only 200. So half. But proportionally, the thickness of this double layer in kaolinite is much smaller to the total size of the clay ion compared to the thickness of the double layer in montmorillonite to the size of the ion for montmorillonite. So that's why the double layer is going to definitely govern the behavior of the montmorillonite here, because the double layer is so much thicker than the thickness or the mass of that montmorillonite ion. Another thing would be the pH of the water. The temperature of the water, the higher the temperature, the larger the thickness, the greater the thickness of the double layer. And then finally is what we call the dielectric constant. Okay, this is, in other words, a measure of how readily a particular fluid can transmit electrons or electricity. So water has a dielectric constant of about 80. Water can transmit electricity pretty well. Okay, it's a good conductor. Check out benzene. Only 2. Benzene can't conduct electricity very well. So the smaller the dielectric constant, the smaller or thinner the double layer. So how does the double layer impact how the clay molecule attracts or interacts with other clay molecules? I like to tell my classes that I like to think of clay molecules and their double layers as college students wearing those those bumper suits, or like those sumo wrestler inflatable suits, right? They run, you can bump into each other, but really those suits are going to govern the interaction between you and that other student. And no matter how hard you try, it's really hard to overcome the effects of those big inflatable suits. That's why they're so stinking funny for other people to watch. So let's learn a little bit about the effects on this, okay? We have here the spacing of two clay particles. Now there's a couple things going on. On one instance, we have repulsion. Repulsion. In other words, the double layers themselves hate each other. They can't stand each other, and they want to push each other away as much as possible. And the closer you get those double layers together, the more repulsive the force is. So these are called double layer forces. The closer you get them together, the more repulsive they want to become. But that's not the only force in play. There is a Dutch molecular physicist named van der Waal, who discovered a very real and a universal, albeit very, very small, physical force between all particles and all molecules. He called them van der Waal forces, meaning that those all particles want to attract each other. There's an attraction, and that attraction will increase as the spacing decreases, but then it flips and will actually go to repulsion, and the closer you get, you can get some very, very strong repulsion, okay? Now, so we call those van der Waals forces. If we combine those effects, what we end up getting is something that can determine, in essence, the molecular structure of a clay. If the forces that repel are larger than the forces that attract, then the clay is going to be what we call dispersive. The clay particles themselves will not touch one another. The double layers will push all the particles as far apart as they possibly can, and the interactions between the particles will be entirely 100% governed by the interactions between the double layers. Okay? Now, if we get into a spot where, say, the attractive forces are larger than the repulsion forces, then we can have what we call a flocculated clay. And a flocculated clay means that the clay particles do connect and they do touch, and they form a flocculated structure. So there's places where the double layer is weak or thin, and it allows the particles to bond together. So to show a diagram, okay, this guy on the left, this represents what dispersive clay looks like, and this guy on the right represents what flocculated clay looks like. Notice flocculated, you have contacts, okay, contacts, and it always happens where the end of a clay molecule is contacting the side of a clay molecule. That's because clay is positively charged at the ends and negatively charged at the sides. That's how it maintains its electrical balance. If it wasn't so, then the universe would be out of balance and we'd probably all disappear and die. I don't know, I'm just making that up, but you get my point. What does this have to do with you? You're probably wondering that. Well, like I've hinted before, if a geotechnical engineer can understand this fundamental behavior, then we can begin to govern and engineer clay minerals to do what we want it to do. So here's a couple real-life engineering applications. One will be the development of marine quick clays. Marine quick clays have been really problematic in different parts of the world, like areas of Scandinavia, areas of eastern Canada. These clays initially can have some pretty sizable shear strength, but if you disturb them, even just the slightest, they can completely collapse, lose their structure, and become very, very soupy and weak instantaneously. Why is this? Well, it's because the clay originally formed beneath the sea. And beneath the sea, there's a lot of sodium. So the sodium caused a thin double layer and caused the soil particles, the clay particles, to be flocculated. So the marine clays formed in a flocculated manner. But then, through isostatic uplift, or rising of the seafloor above the ocean and exposure to fresh water and groundwater flow and all those things, over time that sodium gets leached out of the clay and gets replaced with other minerals. The thing is, the clay retains its flocculated structure, even though the charges, the electrical charges that formed it, aren't there anymore. So all it takes is a little jiggle, and that flocculated structure can collapse into an instantaneous dispersed structure. And that can result in massive loss and rapid loss of shear strength, and you can get some pretty freaky landslides and things like that. So this is an example, for instance, of what happened in the Rissa landslide in Norway, I believe. This was an example that was shared with me from my good friend and colleague Kyle Rollins at BYU. He told me about one instance of the lagoon that's at Treasure Island in the Bay Area in California. When they were constructing Treasure Island, they wanted to have a lagoon there. Now, the problem is Treasure Island's out in the middle of the salt water. Okay, it's out in the middle of the bay by San Francisco. So how do you get that to be a freshwater lagoon? No matter, you can put as much fresh water in there as you want, and eventually the salt water is going to leach in there and make it brackish, turn it into salt water. So they began to look at the mineralogy of the clay, and they realized that the clay that they had there for the island had a lot of calcium in it. So meaning with calcium, it's going to be flocculated, but it's going to have a very high permeability. And this was the problem. Because of that high permeability, the seawater was leaching through, and it was causing the lagoon to become salty. So they decided to force seepage through the clay. They pumped seawater through that clay, and they just continuously pumped it. Well, check this out. Sodium has a lower charge than calcium, so the second you introduce sodium in the mix, it causes isomorphous substitution. The sodium swaps out for the calcium. It still remains flocculated because both of those minerals tend to produce flocculated clays. So once they did that and they realized, okay, now we changed this clay to be a sodium-based clay, then they pumped fresh water through it. And the fresh water leached out excess sodium, reduced that sodium concentration. And once they reduced the sodium concentration, the clay became dispersive. And because it was dispersive, those double layers sealed up the permeability, and water had a very, very hard time flowing through there. And because it was low permeability, they could put fresh water in the lagoon, and the salt water would not leach into that lagoon. So that's a cool application. Here's another application from Professor Rollins that I thought was really interesting. It has to do with land reclamation. So if the government or any entity is trying to reclaim land and wants to use it, now the native soil at that site might have a high calcium concentration in the clay. But over time, what can happen is water irrigation from farming might have high sodium in it. There's places in the world where the water has a lot of sodium. One example of that is Well, no, I was thinking something else. I'm sorry. I was thinking sulfur. For instance, if I go to Florida, there's a tremendous amount of sulfur in the water. It just has a funny taste and smell to me. I don't like it. Um, but I'm spoiled because I drink the mineral water from the mountains in Utah. So, yes, I guess I'm pretty picky. Anyway, irrigation water might have a high sodium concentration. And so over time, as you irrigate the soil, isomorphous substitution will occur by itself. And what it will do is in the soil, it will create its own lens of dispersive soil, usually at a very shallow depth. Okay? And that dispersive soil will trap all of the groundwater, or trap all the irrigation water above it. In other words, it will perch that irrigation water and won't allow that water to seep down to deeper depths. Well, you might have crops that have roots at deeper depths. And if that's the case, then those roots are not going to get any water because all the groundwater gets perched above that dispersive clay layer. So those crops eventually die because they don't get any water. Now, one of the more popular and common applications is that of lime soil stabilization. This is very, very common in transportation applications. Now, when we add lime to clays, lime has calcium in it, okay? So when you add the calcium into the soil, it begins some different chemical reactions. So first of all, you get drying that starts taking place. When you take water and lime, when mixed with clay, it begins to hydrate, just like what happens with say, concrete. And in that hydration, it releases heat, and that heat will evaporate and dry the soil. So just by adding lime, your clay will lose moisture content. Another thing we'll do is those calcium ions are going to migrate to the clay surface, and then they're going to start to displace and push out the water and other ions. You're going to start to have some isomorphous substitution happening because we're saturating the clay with calcium. In doing so, that soil becomes pretty brittle, friable, and granular. It acts more like a grumpy clay or a grumpy sand or something rather than a really plastic and goopy clay. So that plasticity index of the soil is going to decrease dramatically, and its shrink swell potential also decreases. And this change, folks, happens within hours typically. It's pretty incredible. And then eventually, if you add enough lime and water, you reach stabilization. Okay, the pH of the soil will quickly increase above 10.5. So it becomes very, very basic. Okay, and then that enables the breakdown of the clay particles. Those sheets just break apart, and it becomes very, very brittle and very, very friable. Silica and alumina are all released from the clay particles, and then they react with the calcium and the lime, and they perform calcium silica hydrates and calcium aluminum hydrates. Guess what that is, folks? That's like concrete. They cement the soil. They make it hard. So that process will begin within hours and will continue chemically over weeks, months, and even years. And that resulting matrix of the soil produces a permanent, a durable, and an essentially impermeable layer of soil on which we can build pavements and things that normally don't respond very well to soil that has a high shrink swell potential. So here's some figures I pulled off the internet I thought were pretty interesting. Oftentimes this stabilization technique occurs in these just giant stabilization trains. So you have the lime truck right up front, and all it's doing is it's spraying its lime down on top of the soil surface. Just goops and goops of wet lime mixed with water. And then behind that, you have a modified belly dumper that's actually a belly mixer. So it just picks up the soil, the native soil with the lime, and it just churns it, and then it dumps it out the back. Then you have a compactor that compacts it. Then you have a grader that grades it. Then you have a finish roller that makes it nice and flat and smooth. And then as that train passes, the stabilization process continues over hours, days, and weeks. And then you end up with that, what we talked about, that cemented, hard, impermeable soil layer. So I hope that you guys enjoyed today's lesson. I think it's really, really fascinating, and it shows what many geotechnical engineers in the world today are doing and how they're applying their knowledge of chemistry to improve the geotechnical properties of troublesome clay, minerals, and soils. So with that, thanks for watching, and we'll see you in the next video.